इसको हम बगैर डिले के स्टार्ट करते हैं सर। तो आज का हमारा टॉपिक है वाटर डिस्ट्रीब्यूशन सिस्टम। और our स्पीकर्स और वेबिनार ट्रेनर्स और रजा अली साहब और जुल्कुरनैन साहब फ्रॉम कनाडा। तो सर आपके पास है, अब यू कैन स्टार्ट।
Jazakallah khair. Inshallah, we have already recorded the session, and we are starting right away. It is a 55 minutes recording of the session. So, inshallah, bear with us, and at the end we will take the question. And now we are starting, inshallah.
Thank you.
Sure. Can you see the screen, Dr. Saab? हमारी स्क्रीन आपको नजर आ रही है?
जी जी नजर आ रही है, प्लीज कंटिन्यू।
जी, और आवाज भी आ रही है? अब मुझे कंफर्म कर।
जी जी आवाज भी आ रही है।
आवाज नहीं आ रही। जुल्कुरनैन भाई आवाज नहीं आ रही।
रजा साहब की तो आ रही है, लेकिन जुल्कुरनैन साहब की नहीं आ रही।
जी, अब आवाज नहीं आ रही?
नहीं नहीं नहीं, इसकी आवाज नहीं आ रही, वीडियो की आवाज नहीं आ रही।
वीडियो की आवाज नहीं आ रही, ओके।
उसमें ऑप्शन है उसका, स्क्रीन वो साउंड शेयर करने का।
एक तो पार्टिसिपेंट्स में और ऑप्शन, जरा चेक करके मुझे बताएं रजा साहब के कहाँ पर ऑप्शन है ये।
ठीक है।
जो ऑडियो का जो ऑप्शन है ना, उसमें जो म्यूट जहाँ लिखा हुआ है, उसी में आप देखेंगे तो वो
ओके ओके
सेलेक्ट स्पीकर माइक्रोफोन हो रहा है।
ओके, मैं देखता हूँ। तो इसमें ऑडियो सेटिंग्स में जाना होगा।
हाँ मेरे ख्याल से ऑडियो सेटिंग।
सर पहले तो आप म्यूट म्यूट पे जहाँ पे आप माइक बना हुआ है ना, वो उस पे क्लिक करेंगे तो ऑप्शन आएगा सेलेक्ट द माइक्रोफोन। माइक्रोफोन सेम है सिस्टम माइक्रोफोन या माइक्रोफोन। तो आप सिस्टम माइक्रोफोन को करेंगे तो फिर कंप्यूटर से आएगी समझ।
ओके, लेट मी चेक। सेम एज सिस्टम माइक्रोफोन, राइट?
जी जी
जी जी, आप आएगी। जी, मैं स्टार्टिंग में। अब ठीक है ना? आवाज आ रही थी?
नहीं, आवाज नहीं आ रही।
नहीं, अभी आ रही है?
नहीं।
डॉक्टर जुबैर, आप कंफर्म करें।
नहीं नहीं आई सर, मेरे ख्याल में फिर
नहीं आ
आपको
रही?
शायद शायद आपकी आपकी कंप्यूटर की ऑडियो में जाके देखें वहाँ स्पीकर कौन सा सेलेक्ट है।
मैंने इसको सिलेक्ट अ स्पीकर, सेम एज, ओके, सेम एज मैंने आप इस पे किया, ठीक है। अब आ रही होगी
अभी भी नहीं आ रही सर,
जी।
अभी भी नहीं आ रही सर।
Yes. And our presentation is on this topic today. Webinar presentation outline includes understanding urban water network concepts. That includes water supply process, water pressure in urban network, water pressure zones, how the zones are there, hydraulic grade line, water network types, real life examples include we have picked two cities, a district of North Vancouver and city of Edmonton, and included two presentations in there. And then how the fire hydrant system work, and water distribution system comparison. We have done how the basic system is and how in the advanced world is the water distribution system. And finally, we have included a couple of slides on the water quality. Here is my introduction page. My name is Zulqurnain Abbas, and I'm currently working here in Canada as an independent consultant. And here are my credentials. I have 25 years plus experience, and I have done my master's in civil engineering. Here is my email address.
My name is Raza Ali. I am a civil engineer. I am working as an engineer with the city of Toronto. I did my graduation from Medan University and did masters from NED and University of Waterloo. I have over 30 years of experience. Learning objective. So for this presentation, our learning objective is introduction of water distribution system, concept of pressurized flow in water network, understanding of key terms like water demand, flow, pressure, HGL, pressure zone, water network types. We have given some real life examples like city network examples, water for firefighting, and in the end we will be discussing about water quality. So understanding of urban water system and engineering concepts. This is the episode where we will discuss about these terms, these topics. So water supply system process. So there is a demand, as you can see, on the source water extraction, and this could be groundwater source, this could be surface water source, and water is transported to a water treatment plant. This can be going to some open channel flow like the pipes flow, and at the end we are seeing distribution, and here transport and clear water is receiving at the end.
And the demand is calculated here based on the maximum daily demand plus fire flow. And we know the demand of water is low at night as compared to the daytime.
And here we are showing from water supply system from source to the end user. And you can see there is a storage tank and there is a pump. Water is going from pump to the overhead tank. And from overhead tank, there is a user which is using shower. And as we can see, there is a pressure which is from the shower head to the top of the tank. And this pressure water is coming. And in this slide, we are talking about flows in water supply system. So there are some street wall T's used to take off area for scheduled maintenance, and there is some tracking of pump on and off. From production, water is going through the pipes and the pumps and through reservoirs. As you can see, reservoir A and reservoir B, and it's coming to the consumption, where we can see the water is coming, and there may be some leakage unaccounted for water.
Here I would like to add the street valves are, and we call them T's as well, are normally found on the in front of the houses, where we can shut down the supply to a single house, and even we can we can take off whole a community for a scheduled maintenance of the pipe network. And also the pumping system which we are using here, the pumps they are automatically set on to on when they are at the low level, and they get off when the tank is full. Here is the network configuration. So there are different network available. One is the serial network, where the single line is running from the source. Here in this case is the water tank, and running into through these nodes is running into towards the community. Another is the branch network, where it is the main water main is running and taking the water from the overhead tank, and then the laterals are supplying to the individual users. The second typical network configuration that includes here is the looped network, where all the system is in the form of a loop. So all water is running through the network without any dead end in the pipe network, and this is one of the way how we keep the water fresh and healthy and all the time running. And and here another is the combination of the network, where one part is looped, where the pipes are the network of the water mains is in the loop system, while here in the second part we see the pipes are with the dead ends. So sometimes the dead ends could maybe where the water is just comes to a dead end, and there could be a contamination or environmental issues, as the water is not running through the dead end as it was through this loop system.
So here I would like to give my audience about concept of pressure zone, and as you can see, there is a starting from 2000 feet and goes to 2500 feet. So it's 5 pressure zones. Each has 100 feet apart. So usually what happens, we do 80 feet to 130 feet elevation difference for making a pressure zone. So we can make smaller or bigger, depends upon the situation. But here we are taking a constant difference in elevation of 100 feet, and as you can see here at the bottom, so it's a 40 psi pressure here, and we can use PRV or pump, depends upon the flow direction. And in the second loop we can see 40 to 82 psi, 32 similar pressure zone. It looks like equal pressure is distributed in each zone.
And minimum desirable pressure on the top floor when here is 20 psi, like the water pressure should not be less than 20 psi, otherwise it brings frustration for the users. And next slide is regarding this hydraulic grid line. This is very important concept in water distribution system. So here we see in this water main this flow is running in this direction as shown by this arrow, and then with this formula we can see how the piezometric tube is on the top, and is the water level due to this pressure, it reaches all the way on this level. And in this vertical pipe we see the water reaches all the way to this elevated tank. So in case there are no users and the pipe and the pump is running, so water keeps on adding in this elevated tank, maybe at the night time, and during the daytime when the consumption is more and even the pump is running and the consumption requirement is not being met through the pumping source only, then this additional volume of water comes into play and it starts depleting here, and in the daytime during the peak hours they use it. So here is this is the level how the hydraulic grade line from the source where the pump is water is being pumped is coming with more force, and as it goes down it is depleting down and its head is dropping down. So this is HGL. This is very important concept in distribution in water distribution system. Another example is here when if we see here, this is the water, this is a elevated water tank, and this is Z1 is shown like the height elevation above the ground level or any reference level, and then this is the distribution system, and it runs down into the next elevated tank, but this is at the lower elevation as compared to the first. So now from the top of this and the top of this water line, if we connect with this line, the dotted line, so this shows the hydraulic grade line. So how this is the drop in the head. Delta H is the drop in head and also the drop in energy. Here is it is shown the HGL can be understood using this vertical tower, where the one is this tower, this water storage, where we see this is the minimum level, and this is the in the middle is 160, and on the top where it overflows at 180 meter or distance is the elevation from the base. And this is how the pump is automatically set to trigger at the initial level. It triggers and gets on, and when it reaches to the top level, it automatically stops. And here is the concept how the water is draining out. This one concept was how the water is being filled, and another is how the water is being used now. So we see the water is outflowing through this water main, and this is how as the water goes down. So right in the beginning, there's a head loss happens, and this is the HGL line, and the energy grade line is here. It is running smooth. So this is the velocity head is V square over 2G, and this is the head loss on the top. Net flow is not in any of the water tank is calculated based on the inflow minus outflow. So this gives us the volume curve, how much volume is available and in the water tank, and then head is maximum and minimum water level. Here maximum water level and minimum water level, and pump as I discussed, it triggers automatically on and off, and there's no need for any manual operation for filling of the tanks. And normally in a main of 500 to 200 millimeters to 500 millimeter dia are generally taking off from any of these water sources.
Here we are showing the concept of how real world looks when we model into the a system, like using some software. comparison of real versus model. So here you can see on the left side, so there is a tank and there is a pump and there is some distribution system. So as you can see on the pump side, so from the tank, HGL is going down, and from the pump it raises the HGL to up, and further when the water going to the pipeline, it went down. So HGL is went down, and here we are maintaining HGL in the distribution system. On the model side, here we are showing with the link, and same thing, reservoir, HGL, distribution system, but here you can see steady rise in the HGL. So some software like EPANet is showing pump as a link. So this way we can show to the model. So another way we can see the same thing like in the real world, the same arrangement, and in the model we are representing a pump from a node, and as you can see the node is extending, is pushing HGL like the pump. It's very similar. So software like WaterCAD, WaterGems uses the same analogy like this one, and it's more close to the real system.
And here is an example how this dynamics of a pressurized flow system work here. It is actually a moving sea. We call it a virtual ocean to understand better how the pressurized system in an urban setup work. We see here is like, imagine like this, the sea and ocean, and someone is going through the ocean, like all the people living in an urban setup, like although they are in a virtual ocean living when the pressure is maintained as high as this ocean is. So here is let me try how it work. Yeah, here we see now it is moving. So this we see this is a moving world where this ocean, it is a virtual ocean, pressure is related to depth here. Deeper you go and more water pressure we get here. Water is confined, and the water is confined in a series of pipes. A distribution system has a same relation. A distribution system has the same relation between depth and pressure. Imagine if the water distribution system as a virtual ocean, we live inside it. It stopped, let me, yeah. So it gives an idea of pressure available to the customers to understand how to deliver, it again stopped, how to deliver water to the customers at right pressure. Like here is these are the customers, houses are here, and this is the pipe network going, and all the houses are in the real system, and we see here how there's a maximum depth upon this house, and there's a more pressure on this this house. While this house, it is on the top of this urban geography, and here the pressure would be less as compared to this house. So if the city is flat, it is pretty simple, and all houses will sit at the same level pressure under the virtual ocean. If the buildings are at different level, as we see it here, different topographic level, at the bottom of the virtual ocean, pressure is too high, and at high pressure, pipes and valve system is under constant stress here because there's a more pressure at this level and may cause damage to the pipes and the valves. That's why the high rated material is used here, where there is a high pressure. While on the other hand, the houses which are on the top, it may be frustrating for those customers and users who are on the where the pressure is low and when taking the shower and water is not coming as it should be. So in the large cities, that's why it is wise to make them in the different distribution at the different pressure zones. That's why we divide in the different zones. It makes sense maybe. So here are the valves. We see how these valves come under pressure. When there's a lot of pressure, that's why here we see the low pressure. That's why it's wise to distribute this city in maybe here as we see here. One tank is here and another tank is here. This is one pressure zone. This is another pressure zone. And here we see the urban setup and most of the high rises floors can be see here. The virtual ocean stops here, but still the top floor of the building is high. So the issue is how to raise the water all the way to the top. So here we see the individual pumps below each of the building. So each building has their own pumps to pull up. Another we see here on the top, the workers are working and we see these water tanks here. And the water is running through the gravity. And this is the water towers are cheap, as we see here. The water towers is where it is for storage, and this is a cheap approach where the water is run under the gravity. And this elevated storage tanks here we see they are definite here to stay as it is in the basic system of the Eastern world. It is.
So in this slide, we will show some examples of water network. And because I worked with the district of North Vancouver, so I took examples from there. And this is also, we can say, case study for the urban area of British Columbia. So this is an aerial image of this area. As you can see on the north side, so there are some hilly areas, and on the south side there is a sea, and there is a mountain areas on this area, on this location, and we are maintaining different pressure zones because of the difference in elevation. So one pressure zone cannot meet demand of all the customers of this area. And this is Capilano Reservoir, and as we can see, this Capilano Reservoir has capacity, very large reservoir, and this has huge capacity.
And reservoirs are normally unlimited source of water and selected at the high elevation so that the less energy should be used to raise the water to the high rises. So they maybe this Capilano Reservoir is at the higher ground level, and here from this reservoir we have noted like one water main of 2400 millimeter is taking off.
And there is another reservoir. There are two reservoirs. So this is second reservoir, Seymour Reservoir. And this is also a huge reservoir, and this is taking, this is contributing to the flow to the filtration plant. So next we will talk about the filtration plant.
So this is unlimited source of water again, and at high elevation. And from this we have noted two water mains of 2100 millimeter are taking off.
And this is Seymour Capilano filtration plant, And this plant has capacity of 1.8 billion liters per day. And this is the largest drinking water filtration plant in Canada and is operating since 2009. And this is governed by Metro Vancouver. So Metro Vancouver is an organization which is delivering water and taking wastewater from different municipalities. And this is a federation of 21 municipalities, one electoral area, and one treaty First Nation. And this is very big organization, and many municipalities are fed by this organization. And this is, in this slide, I am going to show you some distribution network, how it looks like, and it's drawn over the imagery. So over aerial photo, I draw this this whole network, and this is available online. So everyone can go and download this distribution network for their learning, or for the presentation, or for the consulting work. So it's giving free of charge.
So this network is available for understanding how the water distribution system is running through this district of North Vancouver City.
And this is pressure zones. There are 26 pressure zones, and here I am showing some elevations. So you can see numbers in elevations, and there are different colors for different pressure zones. So as we can see from north side, so we have hilly areas, so high elevation from north side, and low elevation on south side. South side there is a sea here. So in this slide, I am showing residential block. Is zoom in to the residential block. So there are certain elements you can note it down. For example, there are water lines, there are hydrants, there are service connections. So this is underground system, and this is being laid over the aerial photograph. So this is a typical subdivision of district of North Vancouver. And here are some statistics. Population served 88,000, and there are 21,264 service connections. And here you can see the length of water mains, 363 kilometers. There are 7 pumping stations, and we have 12 water storage reservoirs, and we have pressure reducing system, 35, and there are some samples taken on various areas. So sampling stations are 36, and there are 26 pressure zones, and fire hydrants are 1865. As you can see, there are 26 pressure zones. So we have pumping stations, 7 pumping stations, and we have pressure reducing station, 35 pressure reducing station. This will help us to maintain water pressure zones inside the district of North Vancouver.
Next is the next example is the city of Edmonton, and we have tried to show a typical subdivision as was shown by the district of North Vancouver. So this is another province in Alberta, as district of North Vancouver is in British Columbia. So how the typical network is running in the city of Edmonton. Here is the second example. This is a typical map of a residential subdivision, and this is the zoning map. So how different with the different colors with we can see these are the houses, individual houses, and the communities are built with the green spaces, with the schools and other and the commercial places within. So this is how the zoning is defined like the residential, small commercial setups, schools and everything. So this is how a typical plan of a residential subdivision is. Here is the contour map of the pressure, how the water is running through the this whole community. This is the same map as same plan as we show in the previous slide. So looks like this is this red zone. It has less than 280 kilopascal, or also we can measure in PSI, pounds per square inch. So this is one zone where less than 280 kilopascal is maintained. Then this is the zone where the yellow is here, the 280 to 350 kPa, kilopascal, and this is where all the white is. This is between 350 to 550 kilopascal. So high pressure is available in the pipe network. So customers may be happy, but here maybe sometime it becomes frustrating during the peak hours when there's a lot of consumption that users and consumers get less pressure here. And these lines, they show how the contours of the pressure are drawn here, like on the lowest ground, as we discussed during the virtual ocean example. There is a lot of pressure as it is at the deeper level, and as we get higher and higher, we get less pressure, and ultimately we reach here at the red zone, where is the lowest pressure in the network system. This is the water consumption boundaries during the design. So all the individual phases, how they are developed over the time. So their consumption is calculated, and then on the relevant node, the demand of that area is provided. How much demand is for this phase, how much is for this, and how much is this. So water consumption boundaries are drawn, and the overall calculation for the water demand is made. And this slide shows the water mains network. So how the water mains are running. For example, here we see this is the complete loop running here of this pipe. It is a 600 pipe. It is running, and then here is the source, and here is another source. So from this source and from this source, so water is running through the network and then enters into the laterals, and we can see all the network is looped. We don't see any here, even we can see the loop here, and this is the end is here, because water is always draining down. This is the source. So we see in all this community, there's only all the network is looped, and there is no dead end to this network. And this is the model, how the network is modeled. So we see here the nomenclature we use for reservoir 1 or reservoir 2, and then we give them a different naming like P12, P23 or whatever, and then we give the numbers to the nodes like I100 or I2. So this is how we define, draw all the network in the EPNet, and then we provide, we name each water main and the size of the water line, and some are the major lines and some are the smaller line, and then each individual house is provided with the connection, and the normally connection here is 25 millimeter now. The smallest connection to every single house is a 1-inch pipe is connected to each single individual residence.
Here we are introducing fire hydrant network. So because this for the Pakistani students, this might be something new, that fire hydrants are present here and they are used for firefighting. And one of the purpose of the water distribution system is to get water for firefighting. So this is fire truck, and this is 1000 millimeter dia hose, 150 to 250 meter long,
So this fire truck normally has water hose pipe is here, is folded, and then it is easy to unfold and connect to the closest fire hydrant, and almost we can find the hose up from 150 to 250 feet, almost 100, within 100 feet, and we find almost 100 meters, sorry. We find the fire hydrant, and this pipe is available here. It's 150 to 250 feet long, and we can connect to, and then it is used for fire fighting.
And this is one image I am showing here for a typical street of district of North Vancouver, and this is fire hydrant, red color you can see here, and this is the only thing we can show for this for distribution system, because distribution system is underground, and this is a fire hydrant which can be used for firefighting in case there is a fire here. And this is NFPA classification of hydrants. So, for example, light blue, this is used for the flow 1500 gallon per minute or greater. And the second one is the class A. Its color is green, and the flow range for the water is 1000 to 1499 gallon per minute. And the third one is orange, class B, is 500 to 999 gallon per minute. And the last class 4 is red, which is less than 500 gallon per minute. The purpose of this classification is to know the firefighter how much water can be expected from a hydrant. So he immediately have some idea, and he can find some other colleagues if he need it, and if he need more water, he can connect other trucks with other hydrants.
And one more interesting thing is on every single fire hydrant, on top of it, if we see closely, we can see the rated pressure on top of fire hydrant. Like what would be the what is the pressure running through this typical hydrant here? This is engraved on top of each hydrant here. And these are the some example of we picked from different cities. For example, this light green color, we can see this belongs to City of Calgary here. So City of Calgary has adopted this color with the top black cap on top of it. This is another City of Red Deer has picked this typical form for its fire hydrants. And here we see this yellow color. And we can see this has adopted by the Toronto. And then we see here is this one with the yellow and the blue cap. We see City of Edmonton has adopted this shape. And finally, we see the District of North Vancouver has this shape that was also shown in the red color in one of the previous slides. So normally the demand for industrial and commercial fire hydrants is set at, according to the District of North Vancouver guidelines, I believe, 260 liter per second, which is at 50 psi. So pipe rating, as we discussed previously, when there's a lot of pressure and the network is under high stress of pressure, so we need to have the very good quality of the pipe network system. So normally the material used is good for 150 psi up to 150 psi. The pipe system can sustain the pressure. And fire head lead, as we discussed, is here. Fire hydrant lead is because maybe the water line is running here and there is a lateral of maybe a couple of meters, connecting to this fire hydrant, its lead is 150 millimeter. It should not be less than 150 millimeters, as we discussed for residential. Every connection is 25 millimeters, but for the fire hydrant, it should not be less than 150 millimeter, because there's a more water demand from this fire hydrants. And also from time to time, as the fire hydrants are aging and the system is aging and different pumping system requirement change, from time to time the city conducts the fire flow test on individual fire hydrants, and we can check whatever the requirement is for the nearest fire hydrant, what is the fire flow total pressure, as well as what is the discharge available at that typical particular fire hydrant.
One thing I would like to mention here also, that when we make a model, so model has not its authority or credibility until and unless it's being verified by field result. And the field result comes from hydrant test. So we have hydrant test data, and then we calibrate the model from hydrant test data. So this hydrant also used for using calibration purposes.
Time is connection. We also call them fire department connection, or FDC. So normally here we see this is close to the front of the building, industrial or commercial building, or the high-rise building. We see fire department connection, FDC. So how it works is, like when the fire truck comes in case of emergency and fire is God forbid, if there's a fire in the building, so the fire truck comes and the pumper truck hooks up with this nozzle here, and a fire hydrant is also close by at 100 feet to supplement flow volume for firefighting, because the regular water, whatever is coming, may be less, and the volume water volume requirement is more. So the pumper truck connects to this one and boost it to the next level of pressure, so that the fire fighters could successfully control the fire. Here is the close-up view of the fire department connection here. So how these the fire truck, in case of emergency, they would come and connect it here. So fire department connection is found on high-rises in front of the high-rises, as well as the commercial buildings or the plazas, to boost the pressure with fire truck. So a fire truck pump, the pump is mounted on the fire truck, and which pressurizes the flow through this, and maybe it would be used through the existing sprinkler system to control the fire. Inlet to pipe to pump more water for firefighting through the sprinklers. So these are kind of inlets where the pumper truck connects and pumps more water while it is simultaneously connected with close by a fire hydrant to take control over the fire.
So here we are presenting some comparison between two systems, because we have experience of back home, like Pakistani systems, where we were raised, and then we moved to Canada, and now we have experience to Canadian system. So we are in a good form to present the difference between these two systems. So in the next slide, I am showing the comparison between these two systems, Canadian systems and Pakistani water distribution system. So Canadian water system, I will go first. So it's managed by municipalities or designated organizations. So, for example, District of North Vancouver is taking water from Metro Vancouver and is distributing water by the municipality itself. Pakistani water distribution system is managed by Public Health Department. In Sindh, you know, is managed by Public Health Department. For the rural areas or some cities, or some for the Karachi or Hyderabad, they have separate water boards. So from Canadian water system, we took water from surface source, and in Pakistani we can take water from underground source, or in Karachi from some lakes like this one. And the Canadian water distribution system is gravity based or pressurized or hybrid. It depends upon the situation about the contours of the area. So whether it will be fed by gravity or pressurized or hybrid. And in Pakistan, it's mostly gravity based because it's most of the area is plain areas. So there will be less pressure zones, number of pressure zones over there. And energy management for pumping, fill up storage at night as energy is available and cheap. So usually what happens, pumps run at most of the time at night, where we can save some money. And in Pakistan, as far as we know, there is no energy management system. Maybe some big cities have some system, but smaller cities, I don't expect any energy management system. For surface water source and mainly groundwater source for Pakistani. And one main difference for firefighting is in Canadian system we have fire hydrants, and in Pakistani we have trucks which comes to in the case of fire, which comes and then they are full of water and then they spray water over the fire for fire suppression purpose. So for water quality and quantity, there is monitoring. And for example, District of North Vancouver, they have sampling stations. They monitor water pressure, water quality, water quantity based on weekly basis, semi-annual basis, and every year they report to the authorities, provincial authorities. And for the water quality system in Pakistan, we don't know much about water quality system, but in one newspaper I read there was some not known any chlorine in the samples collected by some person. So usually what happens when we treat water, we put free chlorine inside the water in order to combat with the microbes when water travels inside the distribution system. And average daily demand, this is the designed figure, 300 liter per capita per day, and this figure might vary for different municipalities, but this number is for District of North Vancouver. And this number 246 liter per capita per day, I took this from the Dawn newspaper, and this is valid for Karachi. And for other cities like Hyderabad or Mipohas, there might be some closer numbers to this one. And this is here I am showing some comparison between two systems, and one is satellite on Mipohas. This is where I was raised, and this picture I took from internet. And there is another picture from the Quebec, and this is water storage reservoir. So I would like to show water quality for District of North Vancouver example. water quality modeling,
so this
water network.
Yeah, for this water quality modeling urban network, here we see the water in urban network has invariably same water quality level running throughout the network system. So if we open the tap in the kitchen or in the washroom, water is coming from the same source. And the water for domestic use has the water quality guidelines, which are applicable invariably on the system. And water for commercial use, mass water, and needs, for example, a lot of water is used in bulk quantity for construction sites, so they get the special permission from the city or the municipality, and they could draw from the local fire hydrant, and also sometime for farming when they need the water, so they can get the water there as well. And here for the commercial use, for example, for construction, this is non-potable, like it is not sweet water. It is not good for drinking. So normally the trucks are available for 5,000, 10,000 to 20,000 gallons, and for any commercial activity, construction site, or for the road construction where the compaction is to be achieved, and the water, the soil need to be wet. So normally the order is placed and the water is directly taken from any other source than the municipality water, because that water is treated water and this is the raw water, potable. So the trucks, they deliver the water. So industrial use is also disposable. For example, if we see there is an industry that cleans the disposable bottles, so it is they don't need the sweet water, they don't need the treated water, so maybe they can have another source, like ordering the water using the truck. And the water model, what we can do, as we discussed previously, the chemical units in milligram per liter is used, and the trace node for measurements are for the measurement of the chemical, like chlorine in our case. So it could be modeled how the chlorine runs through the source all the way to the end, and we know as the chlorine runs from the source to the end users, it depletes along the water main line. So this is the chlorination water model, EPANet maybe, or other models. They also regulate the water level in chlorine, and chlorine depletes along the line. And water sampling, as was discussed in the example of District of North Vancouver. So it is there are many testing stations for quality testing, and also at any of the nodes, the residual chlorine can be confirmed.
So here I am showing water quality guidelines which District of North Vancouver follows, and this is good for the British Columbia. And here we can see maximum allowable concentration E. coli or non-detectable per 100 ml. So E. coli is the source of human excreta in the water system. So this we take sample for 100 ml and check whether there is a E. coli or not. Total coliform non-detectable is in 100 ml. Heterotrophic plate count, operational guidelines 500 CFU per ml, turbidity 5 NTU, chlorine 0.04 to 2 mg per liter, temperature aesthetic objective 15 degrees centigrade, and pH 7 to 10.5.
Here we arrived at the end of our today's session, and we welcome your question and answer. And here is a typical beautiful tower where the water is being distributed for a rural community, and this is one of the typical example of the water distribution in the in the rural setup, how this water reservoir on the top is being used to serve this all rural community. So if you have any questions or any clarifications, please feel free to contact me or my colleague. Our emails are here, and also if you would go back to our main slides where our introduction page are, you would find more details and email contact for us. So we conclude today's webinar with this, and we thank you all for listening, and feel free to send your questions, thoughts, feedback on the resource person's email provided on the intro page.
We will love your feedback and any comments. You can send, you can ask question now, or you can send letter on our email addresses. Thanks. Have a good day. Bye.
Thank you very much for your time and very excellent informative presentation we have got today. So I would like to ask my students if they have any question.
आप उर्दू में भी बात कर सकते हैं, अब इनफॉर्मल सेशन है, लैंग्वेज का बैरियर ना रहे।
बिल्कुल। तो असल में हमारी ये एक एक्सपेक्टेशन ये थी कि हम हमारे जो पार्टिसिपेंट आज के हैं वो मेरे स्टूडेंट्स हैं, तो एक ये हमारी तवक्का है कि हम ईपीए नेट से बेसिक से शुरू करें सीखना आपके साथ मिलके, एंड देन वी गो फॉर फर्दर लेवल। तो आपका क्या, आप लोगों का क्या प्रोग्राम है फॉर नेक्स्ट स्टेप, क्या किस तरह से इसको प्रोसीड करना है?
डॉक्टर ऐसा है कि हम जो है अभी हमने एक फाउंडेशन बनाई है, मतलब स्टूडेंट्स को हमने इंट्रोड्यूस किया है कि वाटर सिस्टम कैसे कैसे काम करता है, कनाडा में कैसे काम करता है, पाकिस्तान में किस तरह आगा है। अब हमारी नेक्स्ट जो हमारी प्रेजेंटेशन होगी वो सॉफ्टवेयर पे होगी, तो इंशाल्लाह हम ईपीए नेट ही को यूज़ करेंगे क्योंकि ये फ्रीली अवेलेबल है, कोई इसमें लाइसेंसिंग का चक्कर भी नहीं है।
ठीक है, तो ये मेरे ख्याल में बेहतर रहेगा कि हम ईपीए नेट से ही शुरू करेंगे क्योंकि वो डाउनलोड कर सकते हैं, फ्री ऑफ कॉस्ट है। और फिर वो जो आप क्लोज लूप और ओपन लूप और हाइब्रिड, उस पे देन वी कैन गो कि उसको कैसे एनालिसिस करते हैं और उसको कैसे डिजाइन करते हैं। आई थिंक दैट वुड बी नाइस देन। एक सवाल मेरा है वैसे आपसे कि वो आप अपने फायर हाइड्रेंट्स या फायर नेटवर्क के बारे में बताया, तो ये सिस्टम वाटर डिस्ट्रीब्यूशन सिस्टम से दूसरा एक और सिस्टम होता है या उसके साथ ही कनेक्ट होता है?
साथ ही कनेक्ट होता है।
तो उसको वेरिफिकेशन, उसकी वेरिफिकेशन आप कहना मॉडल की वेरिफिकेशन उससे करते हैं, वो कैसे करते हैं?
ये देखिए डॉक्टर साहब, ऐसा होता है कि हम इसमें जो है ना फायर हाइड्रेंट में टेस्ट करते हैं, ठीक है ना, तो उससे हमें फ्लो और प्रेशर का डेटा मिलता है। उस डेटे को फिर हम कंपेयर करते हैं, हम अपने जो हमारा मॉडल होता है उसके रिजल्ट से कंपेयर करते हैं और फिर जो है ना एडजस्टमेंट करते हैं उसको मैच करने के लिए। इस तरह हमारा जो है ना मॉडल कैलिब्रेट हो जाता है।
ये थोड़ा सा कॉम्प्लेक्स है डॉक्टर जुबैर कि इसमें जो है पूरा जब नेटवर्क अंडरग्राउंड जा रहा है तो ऑलमोस्ट आप जब रेजिडेंशियल में मूव कर रहे हैं तो आपको हर दूसरी गली तीसरी गली में आपको मिल जाएगा एक फायर हाइड्रेंट मिल जाएगा। तो वो फायर हाइड्रेंट इंटरनली इस नेटवर्क के साथ कंट्रोल कनेक्टेड होता है। इन केस के किसी भी उस कम्युनिटी में किसी भी घर में खुदा न खास्ता फायर होती है या आग लगती है, चूंकि यहाँ पर मोस्टली घर जो है वो लकड़ी के बने हुए हैं, वुडन स्ट्रक्चर्स हैं और फायर ऐसे कैच करते हैं कि बहुत ही फास्ट। तो फिर फायर ट्रक वहां पर पहुंचता है, तो वो फायर ट्रक में तो एक लिमिटेड क्वांटिटी ऑफ वाटर आ सकती है, तो वो सारा पानी कैरी करके नहीं आती बल्कि फौरन ही उस फायर हाइड्रेंट से कनेक्ट कर लेते हैं अपने हाउस में। और वहीं से पानी वो आना शुरू हो जाता है। फॉर एग्जाम्पल, हमें अगर अपने घर की टैप से फायर फाइटिंग करनी पड़े तो उसका पानी तो पूरा नहीं आता, वो तो एक बकेट भरने पे आपको 10 मिनट लग जाएंगे, राइट? कि एक घर से जो एक टैप या 2 टैप्स या 3 टैप्स चला ले तो एक एक आपको मैक्सिमम एक जग भर लेंगे अगले 1 मिनट में या 2 मिनट में, जबकि फायर हाइड्रेंट से बल्क क्वांटिटी में आप एक्सट्रैक्ट कर रहे हैं पानी, और चूंकि फायर को तो आपने विद इन मिनट्स सप्रेस करना होता है। तो इस तरह ये पूरा नेटवर्क जो है फायर हाइड्रेंट्स का ये कनेक्टेड होता है। तो हमारा एज ए सिविल इंजीनियर जहाँ तक काम है कि हम उस तक इंश्योर कर देते हैं कि फायर हाइड्रेंट्स तक उतना पानी जितनी उसकी डिमांड है वो मौजूद है। इससे अगला काम फायर डिपार्टमेंट का है। तो हम ये इंश्योर करते हैं कि इस फायर हाइड्रेंट में जो है 1000 से 1500 गैलन पर मिनट के हिसाब से डिस्चार्ज अवेलेबल है, और किसी भी टाइम जो है वो फायर की सूरत में उसको यूज किया जा सकता है।
जी जी। अच्छा, ये एक और बात मेरे ज़हन में आ रही थी कि ये टोरंटो या वैंकूवर में अभी तक क्लोरीनेशन ही एक जरिया है उसका डिसइंफेक्शन का, या कोई और भी केमिकल यूज होते हैं?
नहीं, हम यहाँ पर जो है ना, बहुत सारे इलाकों में यूवी डिसइंफेक्शन भी होती है, अल्ट्रावायलेट क्लोरीनेशन के साथ साथ।
तो लेकिन उसका रेजिडुअल तो नहीं होगा, तो रेजिडुअल के लिए फिर क्या करते हैं?
ये क्लोरीनेशन ही यूज करते हैं residuals के लिए।
अच्छा, यूवी के बाद।
जी जी।
अच्छा डॉक्टर साहब, अपना अली साहब, एक मेरा सजेशन ये है कि क्योंकि हमारे पास स्टूडेंट्स हैं और होपफुली के बाद में और भी ज्वाइन करेंगे, तो हम थोड़ा सा इसको स्टूडेंट क्लासरूम वाला माहौल अगर बनाएं तो ज्यादा बेहतर है कि आप उन्हें कोई रीडिंग मटेरियल भी दें या रेफरेंस बुक बता दें कि वो उससे पढ़ के आए, या कोई एक्सरसाइज उन्हें दे दें होमवर्क के तौर पे। वो ज्यादा बेहतर हो जाएगा। फिर वो जब नेक्स्ट टाइम आपसे मीट करेंगे तो उन्हें कुछ उनकी नॉलेज और स्किल बढ़ चुकी होंगी। तो क्योंकि प्रेजेंटेशन बस वही लिसन और बस उसके बाद फिर क्योंकि होमवर्क कुछ नहीं होता या कोई एक्सरसाइज नहीं होती उनके पास, तो students cannot increase their learning.
जी बिल्कुल, आपने दुरुस्त कहा है। तो इस पे नंबर 1 तो अगर आपने रिकॉर्ड कर लिया है तो इसको अपने तौर पर एक सेकंड टाइम इसको लिसन करें, और उसके अंदर जो जो रेफरेंसेस ईपीए नेट के हो गया या नेटवर्क सिस्टम का, उसको अपने तौर पर गूगल पे जाकर जिन जिन सिटीज का हमने जिक्र किया उनको जाके देखें। फिर उसके स्ट्रीट व्यू में जाके आप इनको देख सकते हैं अपने तौर पर। इसी की के फॉलो अप में आप गूगल मैप है, उसके थ्रू आप इसको सर्च करें तो स्टूडेंट्स कैन एनहांस देयर कैपेबिलिटी अंडरस्टैंडिंग ऑफ दिस नेटवर्क सिस्टम। और स्टूडेंट्स भी फील फ्री टू टॉक, बिल्कुल कोई क्वेश्चन, ऑल क्वेश्चंस आर वेलकम प्लीज।
थैंक यू फॉर द प्रेजेंटेशन। मेरा एक क्वेश्चन था कि जब वाटर डिस्ट्रीब्यूशन सिस्टम हम बनाते हैं तो उसमें वेदर जो चेंजेस आती रहती हैं थ्रू आउट द ईयर, तो उसकी क्या कंसिडरेशन हम ड्यूरिंग द डिज़ाइन लेते हैं वाटर डिस्ट्रीब्यूशन सिस्टम? क्योंकि आप कनाडा की बात कर रहे हैं तो वहाँ पे कभी कभी हेवी स्नोफॉल्स भी हो जाती हैं, तो उसके हिसाब से क्या मेजर्स लिए जाते हैं?
बहुत ही इम्पोर्टेंट क्वेश्चन आपने किया है कि सबसे पहले तो इसमें हम ये देखते हैं कि हमारी जो वाटर लाइंस जा रही हैं वो एक सर्टेन डेप्थ पर जा रही हैं। आजकल अभी जो है नेक्स्ट वीक यहाँ पर मैं कैलगरी में हूँ और रजा इस वक्त टोरंटो में है। कैलगरी में नेक्स्ट वीक टेम्परेचर वुड बी अराउंड -20 तक जाएगा, इवन विंड चिल के साथ -30 तक जाएगा। तो इट विल बी टोटल एवरीथिंग विल बी फ्रोजन अप। तो सबसे पहले तो इस चीज को कंसिडर किया जाता है कि जो ही आपकी लाइन जो है वाटर लाइन जमीन के करीब पड़ी हुई होगी तो वो फ्रीज हो जाएगी। और आपको पता है कि जैसे ही कोई चीज फ्रीज होती है, जैसे हम बर्फ रखते हैं अपने फ्रिज के अंदर, तो उसके बाद वो फैल जाती है, उसका वॉल्यूम बढ़ जाता है। तो मोस्टली वो वाली पाइपलाइंस जो जमीन के बिल्कुल करीब होती हैं और उनकी डेप्थ प्रॉपर नहीं होती, वो पाइपलाइंस फट जाती हैं। तो सबसे बड़ा इंपॉर्टेंट प्रॉब्लम यहाँ पर यह है कि जब हम उन लाइंस को बैरी करते हैं अंडरग्राउंड तो मेक श्योर करते हैं कि एटलीस्ट 1.5 to 2.5 मीटर डीप हो अंडरग्राउंड हो पाइप, ताकि वो टेम्परेचर एक वो फ्रीजिंग जोन में ना चली जाए। तो हर सिटी का, चूंकि अल्बर्टा का डिफरेंट वेदर है, ब्रिटिश कोलंबिया रिलेटिवली माइल्ड है, वहाँ पे इसका जो स्टैंडर्ड है वो डिफरेंट है। वहाँ पे अगर 1 मीटर पे भी पड़ी होगी तो फ्रीज नहीं करेगी। और यहाँ पर जो है वो होता है। और ज्यादातर जो वाटर प्रॉब्लम्स आते हैं अल्बर्टा प्रोविंस के अंदर, चूंकि यहाँ पर टेम्परेचर बहुत डाउन जाता है, तो उस वक्त जो है मोस्टली पानी की पाइपलाइंस फट जाती हैं, बस्ट होती हैं विंटर में। तो फिर पूरी की पूरी, हमने उसमें जिक्र किया कि पूरी कम्युनिटी को हमें टेक ऑफ करना पड़ता है, उसको शट डाउन करना पड़ता है, उसको सोर्स से जाके वाल्व बंद करना पड़ता है। तो पूरी एक मोहल्ले की समझ लें या पूरी एक कम्युनिटी की, चूंकि पाइप फट गया वो स्नो की वजह से, उसके अंदर पानी जो था वो फ्रीज हुआ और लाइन फटी, तो अब पूरे का पूरा वहां पर फ्लड आ गया या एक तो पूरी उसको टेक ऑफ कर लेते हैं, उस कम्युनिटी को बंद कर देते हैं और फिर ट्रकिंग के थ्रू घरों तक पानी पहुंचाते हैं। और जब तक उसकी मेंटेनेंस हो, 2 दिन लगे, 1 वीक लगे। तो ये बड़ा इंपॉर्टेंट है कि वेदर के हिसाब से वी हैव टू टेक केयर, और उसके हिसाब से तमाम स्टैंडर्ड्स जो है वो सेट करते हैं।
तो बिल्कुल सही है। अच्छा, इसमें मैं और चीज़ ऐड करना चाह रहा था कि ड्यूरिंग द डिज़ाइन फेज जब हम वाटर ट्रीटमेंट सिस्टम, डिस्ट्रीब्यूशन सिस्टम डिज़ाइन करते हैं, तो वहाँ पे पाइपिंग मटेरियल वगैरह ये कंसिडरेशन दी जाती है वेदर के हिसाब से। तो कुछ मटेरियल्स ऐसे होते हैं कि वो होल्ड नहीं होते, तो ये पाइपिंग मटेरियल या डिज़ाइन फेज में हम क्या कंसिडरेशन लेते हैं, ये मुझे थोड़ा
जी, मैं भी, मेरे बात रजा भी कुछ ऐड करेंगे। तो इसमें ऐसे है कि पुराने पाइप जो है वो कास्ट आयरन के थे, जो 50s और 1950s और 1960s के थे। लेकिन अभी जो लेटेस्ट पाइप्स हैं वो हम पीवीसी के या यूपीवीसी के पाइप हैं, या अगर IPEX आप लिखें, IPEX, तो ये एक स्पेशली रेटेड पाइप्स हैं। ये अब हम यूज करते हैं यहाँ पर। जो लेटेस्ट जितना डिजाइन है उसमें हम इन पाइप्स को रिकमेंड करते हैं कि यूपीवीसी का 25 मिलीमीटर का पाइप यूज होगा, और यहाँ पर जो है कास्ट आयरन का पाइप यूज होगा। लेकिन मोस्टली अब पीवीसी के पाइप्स यूज करते हैं। नंबर 1। नंबर 2, उसको प्रेशर जोन के हिसाब से भी देखा जाता है कि जैसे हमने वर्चुअल ओशन की एग्जांपल में देखा कि जो घर सबसे नीचे था उस पे सबसे ज्यादा प्रेशर था, तो वो पाइप्स जो है ऑलवेज उन पर वो बड़ी हाई स्ट्रेस में रहते हैं। तो उनके लिए हम अच्छी क्वालिटी का हाई रेटेड मटेरियल यूज करते हैं। फॉर एग्जांपल, वहां पे हमें एक्सपेक्ट कर रहे हैं कि यहाँ पे 100 PSI से प्रेशर बढ़ जाएगा, तो वो वाला पाइप यूज करेंगे जो 100 PSI के प्रेशर को सस्टेन कर सके। जबकि एक घर जो है वो पहाड़ी के टॉप पर है, तो वहां पर प्रेशर ही 20 से 40 PSI तक रहता है। तो वहां पर जरा नॉर्मल क्वालिटी का, हल्की क्वालिटी का पाइप भी चल जाए। तो एग्जैक्टली उसको हम अकाउंट फॉर करते हैं।
अच्छा, इसमें हम ऐसा भी करते हैं कि स्पेसिफिकेशंस में डिफाइन कर देते हैं कि किस किस्म का मटेरियल यूज होगा। तो कुछ कंपनियां हैं मतलब जो फेमस हैं, तो आमतौर पर उन्हीं के मटेरियल यूज किए जाते हैं। अच्छा, दूसरी चीज ये है कि जब हम डिजाइन फेस कर रहे होते हैं ना, तो हम एवरेज डे डिमांड, मैक्सिमम डे डिमांड, पीक आवर डिमांड, इन तीनों डिमांड को सेटिस्फाई करने के लिए जो है ना, हम अपना पूरा नेटवर्क को डिजाइन करते हैं। तो इस चीज का हम खास ख्याल रखा जाता है। फिर जब फायर फाइटिंग के लिए भी फिर हम चेक करते हैं कि फायर उस वक्त हमें इतना अवेलेबल फ्लो है या नहीं। तो ये सारी चीजें जो है ना, हमें हमारी जो है स्पेस उसमें सिटी की गाइडलाइन में डिफाइन होती है।
थैंक यू।
वेलकम।
कोई और स्टूडेंट?
अगर किसी और का कोई सवाल नहीं है तो फिर मेरे ख्याल में कंक्लूड करते हैं। मैं रजा अली साहब का और जुल्कुरनैन साहब का बहुत मशकूर हूँ, आपने ये इनिशिएटिव लिया और टाइम हमें दिया। तो मेरा ख्याल में अगर आप मुझे नेक्स्ट टॉपिक, नेक्स्ट सेशन के लिए और उसकी कोई अगर प्री रिक्विजिट है वो मेल कर दें, तो और टाइम भी और किस वक्त आपके लिए कन्वीनियंट है, तो फिर हम उसी तरह से अरेंज कर लेंगे।
हम प्लान कर रहे हैं डॉक्टर साहब के एक जैसे ये वाटर पे हुआ है तो एक मजीद सैनिटरी पे हम करें और एक स्ट्रॉम पे कर लें, और फिर ताकि एक इंट्रोडक्टरी लेवल के और अंडरस्टैंडिंग लेवल के, प्रिलिमिनरी अंडरस्टैंडिंग के तीनों वेबिनार्स आपके लिए मौजूद हों और आप स्टूडेंट्स को रेफर कर सकें। और इन फ्यूचर जैसे आपने कहा कि EPA नेट पे या किसी थीसिस पे स्टूडेंट्स को ज़रूरत है, तो वो इंडिविजुअल बेसिस पे वी कैन हेल्प, वी कैन बी एडवाइज़र और थीसिस में हेल्प कर सकते हैं, या इंडिविजुअल क्लासरूम की फॉर्म में अगर करना चाहे तो वो भी हम कर लेंगे। तो एक प्रीरिक्विजिट है डॉक्टर साहब के, वो ये है कि वी वुड रिकमेंड के जो PC स्विम है, PC स्विम यहाँ पर वो यूनिवर्सिटीज को PC स्विम की जो सॉफ्टवेयर कंपनी है वो फ्री ऑफ चार्ज देती है। तो हम आपको एक ईमेल कर देंगे, तो प्लीज़ प्रोसीड और वो आप उनको रिक्वेस्ट भेजें PC स्विम वालों को जो ये टोरंटो बेस्ड है, और उनसे रिक्वेस्ट करें कि हम इस तरह जो है हमारे स्टूडेंट्स यूनिवर्सिटी के आर इंटरेस्टेड टू लर्न द PC स्विम और वाटर, तो उसमें हमें जो है सॉफ्टवेयर जो है उसका लाइसेंस वो दे गिव इट फॉर फ्री टू द यूनिवर्सिटीज।
ठीक हो गया।
डॉक्टर साहब एक चीज का और मैं इजाफा कर दूं कि PC स्विम जो है ना, उसमें EPA नेट और EPA स्विम दोनों को साथ लेके चलता है। मतलब ये है कि अगर आप EPA नेट का कोई में काम करना चाह रहे हैं, उस पर भी काम कर सकते हैं। उसको उठा के PC स्विम में लेना चाहें, PC स्विम में ले जा सकते हैं। PC स्विम का एक एडवांटेज ये भी है कि इसमें जो है ना वो शेप फाइल वगैरह जो है वो भी आ जाती है। मतलब ये GIS सिस्टम भी इंटीग्रेट हो जाता है।
ठीक हो गया, ये अच्छा हो जाएगा। ठीक है, आप सर मुझे मेल कर दें तो मैं उनको रिक्वेस्ट कर दूंगा, और साथ में अपनी जो भी आपने सेशन करना है, जो सेवेज कलेक्शन का या दूसरा भी, तो उसकी थोड़ी सी डिटेल भी थोड़ा सा भेजिए ताकि मैं उसको थोड़ा सा एडवर्टाइज करूँ।
जी जी, वो हम अपनी तस्वीरें भेज देंगे, आपकी रिक्वेस्ट मिल गई थी, इंशाल्लाह जरूर।
ओके, थैंक यू वेरी मच।
जी वेलकम।
जी इंशाल्लाह वी आर प्लानिंग के जनवरी में एक सेशन रखा जाए जो सैनिटरी नेटवर्क भी हो इंशाल्लाह।
ठीक हो गया, थैंक यू। फिर आपके ईमेल का इंतजार रहेगा
इंशाल्लाह। थैंक यू वेरी मच। अस्सलाम वालेकुम।
वालेकुम सलाम, बहुत बहुत शुक्रिया, थैंक यू। अल्लाह हाफ़िज़।